Hi, Algebra 2 Honor students. This is going to be Unit 7, Day 2, and today we're looking at the concept of quadratics as they involve nature of the roots. So we talked about finding roots in yesterday's lesson. In the first part of the lesson, by the way, this is on page 16 in the packet, so all of the notes today will be included in the packet. And the directions on page 16 say, in the examples below, determine the roots algebraically by using the quadratic formula. So here's quadratic formula right here as a quick reference. And it's super important that you use quadratic formula for all of them, not only because it's good practice to use this, but I'll tell you, you're going to find that some of them are even factorable. But you can't factor to be able to make conclusions later in the lesson about what's called the nature of the roots. And the nature of the roots is just kind of like, what kinds of roots are we talking about here? Okay, are they real roots? Are they non-real? Are they rational? So those are some of the words we're going to use to describe the roots later on. But in order to have this make sense, you have to use quadratic formula for each of these. So take a look at these first two examples. I'm going to encourage you right now to pause the video and try these first four examples. Do quadratic formula, get the roots, and then once you're done, hit play again and check back with my answers. But these are all things that you should know how to do from yesterday's lesson, and hopefully we have a good solid foundation of quadratic formula. Okay, so if you're hitting play again, here are the answers to the first two. So subbing in A, B, and C to the original quadratic formula. When I simplify, the most important part of this process is really that number underneath the radical. We want to make sure that we're getting that correct when we simplify. Now, when you do that, you can use a calculator if you'd like. But going from there, in this case, the square root of 0 is still 0. So over here, square root of negative 36, we're hopefully pretty good at this point to say that that's 6i. And then from there, we're going to go ahead and split up the plus or minus. So on this side, negative 6 plus or minus 0 is still negative 6. So negative 6 divided by 2 is negative 3 twice. So that's kind of a unique case here because adding and subtracting 0 didn't change this number. Here, when I divide 2 into both of those terms on the top, we're going to get 4 plus 3i and 4 minus 3i as the two roots. So we do get imaginary roots or complex roots, right? They're of the form a plus bi. And I hope that you've already gone through the practice for numbers 3 and 4 as well. So there's different scenarios for how the roots turn out in these cases. In number 3 and number 4, here's my initial substitutions into quadratic formula. Number 4, by the way, was the only one that is going to have a denominator other than 2 when I simplify, right? Because 2 times 2 would be 4. So make sure we don't lose track of that. This wound up becoming the square root of 8. Here we got square root 49 for the numbers underneath the radical. So simplifying gets you to this stage. Whenever you have a radical that's not a perfect square underneath, like 49 was, my expectation is that you will at least simplify the radical. And then in this case, 2 divides into both of those evenly. So we get 3 plus and 3 minus radical 2. And then finally on the other side, we do get, like we said, since 49 was a perfect square, we get that nice rational value here. 5 plus 7 is 12, divided by 4 was 3. 5 minus 7 is negative 2, divided by 4 reduces to the other root of negative 1/2. So hopefully you got some good quadratic formula practice in. You should be definitely an expert at using the quadratic formula to find the roots. So how does this all play into today's lesson on the nature of the roots? If you turn to the next page, on page 17, we have some nice trees at the top as my play on words with nature of the roots. But what we have is, for the quadratic formula at the very top there, it says the expression under the radical in quadratic formula is known as the b squared minus 4ac value. It's known as what we call the discriminant. So it has a special name. And the discriminant, that b squared minus 4ac value, can tell you a lot, just that singular number, about what kind of roots we have in the end. And there really are going to be 4 different cases, right? If you look at these roots, it may not look like we're looking at 4 different scenarios here, but there's a very specific reason that I chose each of these examples, because the roots turn out in 4 different ways as we compare those 4 results in the end. So in order to start uncovering what those 4 different ways that the roots can turn out are, we're going to talk about, in this chart, the value of the discriminant. So I'll put that in the left column. So the first example, the number under the radical was 0. Then we're going to talk about, well, how did the roots turn out there? And I've already sketched the graph over here for you about what that will look like. So when the discriminant was 0, if you flip back for a second, the discriminant was 0, the roots were -3 and -3. So the first question is, are they real or imaginary? Well, -3 last time I checked is a real number. Are those numbers rational or irrational? Well, -3 is also a rational number. Irrational would be, unending, non-repeating decimal, usually has radicals involved. All right, and then finally, are the roots equal or unequal? Well, the roots are equal, aren't they? We got x equals -3 and x equals -3, which is why you can see the graph over here. When you sketch that function, it kind of bounces off the x-axis at x equals -3. So that's how I would classify the roots. The nature of the roots for that specific quadratic was that they are real, rational, and equal. Okay, moving on to -36. So -36, when that was the discriminant in number 2, the roots were 4 plus 3i and 4 minus 3i. So that first question, real or imaginary, here the roots are imaginary. And are they rational or irrational? That only applies if the roots are real. So we're going to cross that off. And it turns out that those were unequal. One was 4 plus and one was 4 minus 3i. And if they are imaginary, by the way, the roots will always be unequal. So that's just kind of a quick aside that if they're imaginary, they're always going to be 1 4 plus, 1 4 minus. In fact, we know that term already. They're always going to come in a conjugate pair. Okay, so that will be something that's pretty big to us in this unit. It might be tough to tell based on the light, faint grid lines here, because the x-axis would be like way down here if I were to draw it in. If you can look at the scale on the x-axis, the y-axis, this is y equals 10 and y equals 12. So the lowest point it looks like is at y equals 9. We're definitely not crossing the x-axis. So I want you to start making some conclusions about, okay, this was the discriminant, the number under the radical. The roots are imaginary, and here's what that graph looks like. Okay, moving on, the next discriminant was 8. How did those roots turn out again? For number 3, it was 3 plus and 3 minus radical 2. Well, 3 plus and 3 minus radical 2, since as long as they don't have any I components to them, we know that those roots are real. Those are real numbers, but they happen to be irrational. Right? Radical 2 is a decimal that doesn't end, doesn't repeat, so we got to make sure that we classify now the roots are irrational, and they also happen to be unequal. 3 plus radical 2, 3 minus radical 2, just different numbers. So what we notice about the graph is that those are two distinct places on the x-axis. 3 minus radical 2 is going to be, I don't know, somewhere in the ballpark of 1 point something, right? Like it's probably like 1.6-ish. And then 3 plus radical 2 is about 4.4-ish. So they're going to cross at these decimal approximate locations, but we do cross the x-axis twice. And that's going to be a conclusion I want you to start making. Because remember, in the first case, we only hit the x-axis once. Here it was 0 times, and then here it's twice. Just at maybe not such nice low decimal values. Okay. Finally, we're on to the last case. What were the roots when the discriminant was 49 under the radical? When it was 49, it was 3 and -1/2. Well, last time I checked, those are real roots. Those are real numbers. They are also rational numbers, but they are unequal. They are not the same. So if you look at the 4 cases that we've uncovered now, they're all different scenarios. Here it was real rational as well, but those were equal roots. In fact, the only time you'll ever get equal roots is when that discriminant is 0. Every other time, if you look down the line, it's unequal, unequal, and then unequal. So when you get up this number right here, 49, real, rational, unequal, and the roots, we can confirm -1/2, +3. Yep, those look like the correct locations according to the roots we found with quadratic formula. So what we have to do now is start making some conclusions about what kinds of numbers are these, and how does that type of number determine the nature of the roots, what kind of roots we get, and then maybe even what the graph looks like based on that. So what I'd like you to do is turn to the next page. So we're on page 18 now, and we're going to generalize the 4 cases for the nature of the roots. So for the discriminant, if we have b squared minus 4ac, that again, it's the number under the radical, if that equals 0, what wound up happening? Well, when we saw that we got 0 under the radical, the roots turned out to be real, rational, and equal to each other. real, rational, equal roots. And the reason why is when we have negative b plus or minus that 0, that negative b plus or minus 0, adding and subtracting 0 to something won't change the b value up front. So that's why the roots turn out to be equal. And it says, what's a general sketch of what the graph might look like if we have equal roots? Anytime you have equal roots, you're going to bounce off the x-axis at whatever that equal root is. So you don't actually cross the x-axis, you kind of bounce there. A fancy name for that is that we're tangent to the x-axis at that root. So if you want to be fancy like me, you can say we're tangent to the x-axis there. What was the second case that we saw? Well, when the discriminant was negative 36, the way we were going to generalize that case is that b squared minus 4ac is less than 0. And when you have a negative number underneath the radical, then the roots are automatically imaginary. And that should make sense to us, right? Square root of a negative is definitely going to be imaginary roots. Imaginary roots are always unequal. So what might a graph look like that in the end, if we determine the discriminant's negative? What kind of graph might we see? Well, just one that hovers above the x-axis completely. You cannot cross the x-axis ever if you have imaginary roots as your solutions, okay? So just know that we're not going to cross the x-axis at all under those circumstances, okay? So then we have two more cases here. One is that we're a positive number, but we have to break positive down into two separate cases. One is a positive number that's a non-perfect square. And then if we have a non-perfect square, we'll also have a perfect square that goes with it, okay? So the positive number that's not a perfect square, what happened in that case? This was the example where the discriminant was 8 before. The roots were real. And then we have not rational, but now they are irrational and unequal. Okay. So if we think about what the graph looks like, you will cross in two places. But those two places that you cross are kind of ugly decimals. Okay, so they're not such nice looking locations. They're just going to be kind of these irrational and what I would call, it's not very nice of me to say it, but we'll call them ugly decimals. All right, so then the final case is if the discriminant is positive, but we have a perfect square underneath the radical, like that 49 case, the roots are definitely real, but now they are rational. They're going to turn out to be nice numbers, and they are still unequal. So the graph pretty much looks the same as what we had for irrational, but I'm going to call these kind of like nice numbers. Okay, things that are, you know, whole numbers, integers, even fractions, I would still consider to be nice numbers, right? Like -1/2. We should still be pretty happy about that. So these are the four key cases. We've got to know these because other than actually finding the roots altogether, sometimes questions are asked just about this discriminant. And you might have a question that says, don't actually find the roots, but tell me about the nature of the roots. What kind of roots would we expect? Are they real or imaginary? Are they rational or irrational? And finally, are they equal or unequal? But remember, the only time you ever get equal roots is that first case when the discriminant is 0. All other cases, you will not get equal roots. Okay, I'm going to do, oh, the doorbell just rang at my house, so that's not good timing for my dogs barking. So I'll pause here for a moment while they bark at the doorbell ringing. Okay. All right, let's keep going on. I think they're over the doorbell ringing. In the examples below, it says determine the value for the discriminant and then the nature of the roots. So remember, the value of the discriminant is just the value for b squared minus 4ac. So I'll do a couple of these with you and then let you try a few on your own. So in this example, if we have a is 1, b is 3, and c is 1, the discriminant would be 3 squared minus 4 times 1 times 1. Okay, so if I clean that up, we get 9 minus 4, which is a total of 5. If the discriminant is 5, what kind of number is 5? Well, 5 is a positive number, but it also is not a perfect square. So if we use this chart as a guide up there, we should know that in the end, the roots will turn out to be real, they'll be irrational, and then also unequal to each other. So these, I think, will go pretty quickly for us once you kind of get the hang of it. In number 2, 3x squared plus 11x minus 20. If we do b squared minus 4ac, b in this case is 11. Okay, so we get 11 squared minus 4 times 3 times negative 20. So this is going to be 121. And then you're going to get a plus over here. That's going to be 12 times 20, which is 240, for a total of 361. And I actually think this, because of the large number that we're working with here, well, we definitely know it's positive. So we're going to go with one of these two cases. But we have to check whether or not it's a perfect square. And you can do that quickly by taking the square root of it and see if it comes out to be an integer. And it actually turns out that 361 is a perfect square. It's 19 squared. So because this number is a perfect square, the roots are real, they are rational, but remember, they're still unequal. The only time you get equal roots is when you get a 0 as your answer there. Okay, I'll jump down and do number 4. I'll let you guys try number 3, and we'll go over that next time I see you in class. But for number 4, x squared minus 5x plus 9. We'll go ahead and do b squared minus 4ac, so negative 5 squared minus 4 times 1 times 9. So there's going to be 25 here. That's 25 minus 36. 25 minus 36 is negative 11. So if the discriminant value is negative, what does that tell me about the roots? Definitely that they are imaginary. And imaginary roots are always unequal. Like I mentioned earlier, imaginary roots always come in that thing called a conjugate pair. Okay. One more thing to do left on page 19. We're going to work on number 1 at the top, and then I'll tell you number 2. We'll save that for class. So if you want to try it on your own, I'll kind of leave that up to you. I definitely want you to try number 3 before you come to class. But for that last question for number 2, all those different components, I'll leave it up to you if you wind up doing it before class or not. All right, so applying the discriminant given this equation, x squared plus, kx plus 100. So we're missing the constant where b is, right, equals 0. Determine all possible values of k that make the roots the following: equal, real and unequal, or imaginary and unequal. Okay, so when we go with the equal case first, this actually is going to be the easiest case. We know that in order to make the roots equal for this, it's a discriminant question. The only way to get equal roots is if the discriminant is equal to 0. So what we're going to do is we're going to sub in that the value of b is k, and that's what we're trying to find, right? We're trying to figure out what values of k make this true. We know that a is 1, and we know that c is 100. So go ahead and plug in there, k squared minus 4 times 1 times 100. Okay. So we get k squared minus 400 equals 0. You have really 2 paths you can take at this point. You can, at this point, add the 400 over, square root, or you can factor this because it does happen to be difference of perfect squares. So I'll take the first root of adding the 400 over, but just be very cautious that when you do that, when you take the square root of both sides, don't forget it is plus or minus 20. Okay. So if k is positive 20 or if k is negative 20, you would get a quadratic with equal roots, because essentially what's happening there, if you think about the graph, and I'm just going to show you what the graph would look like up here. In one instance, you might get a value of k on the negative side of the x-axis with equal roots like that. And in the other instance, you might get a value of k, right? It could be one of those two cases. So if k was negative 20, we would actually go, it would be a shift to the right, actually. If k was positive 20, it would shift the graph to the left and look like this. Okay. All right. So then what do we do for these last two cases? Well, here it says, what if it's real and unequal? If the roots are real, but they're not the same, all we know is that the discriminant is some positive number. Notice how I didn't even split rational or irrational there, because it doesn't matter. It's going to be a whole range of values that satisfy this for my values of k. And similarly, if I want to know when the roots are imaginary, that's when the discriminant is less than 0. So what we're trying to solve here, since we've already done a, b, and c, subbing that in, right? This is k squared minus 400 is greater than 0. And this would be solving where is k squared minus 400 less than 0. And what turns out to be in this case is that it's a case where we need to partition. Right? We actually solved quadratic inequalities in Unit 6 not too long ago, so I hope this is something we remember how to do. The two solutions when this equals 0, we already know, are plus or minus 20. So those are what's going to go on the number line. And if you do the partitioning here, if you test something, let me actually just come to the middle quick because that's easiest. If I test 0, 0 squared minus 400, well, that's definitely a negative number. If I test something outside of negative 20 and positive 20, squaring a number, remember this is 20 squared, isn't it? 21 squared minus 20 squared is definitely going to be a positive. And even if I choose negative 21 squared is a positive number. So minus 400 will still make that positive. So how do I use this? I can actually use this number line to answer both of these questions, can I? So for the inequality on the left side here, we're looking for greater than 0. So here we're looking for positive. If you choose a value for k that's from negative infinity to negative 20, or from 20 to infinity, that's going to make this have real but unequal roots. If on the other hand, you choose a value of k that's makes this less than 0, which is we want negative in this case, any value between negative 20 and positive 20 would make it such that the roots are imaginary. And here's the great thing. We can always check that, can't we? I can pick, whatever I want here in between negative 20 and 20. I could pick 10. If I plug in 10 for the value of k and I graph it on the calculator, I should see that it doesn't cross the x-axis and that the roots are imaginary. But if I pick a value like maybe I said before, 21, which is outside of this interval in the middle, if I pick 21, what should happen? Well, when the roots are real but unequal, it's going to cross twice. So anything in this range, the parabola would not cross the x-axis at all. And then in the middle section, it would actually cross twice. So a lot of excitement in today's video. We had some dogs barking, some doorbells ringing. But next time I see you, we're going to take a look at, we're going to do number 2 together. So again, if you want to try this, feel free to do that. Otherwise, enjoy the rest of your day and a lot more to come with quadratics.